Hello students, welcome to AriserTalent. I am Arpita Sharma, your math teacher. Now, we are discussing chapter 1 of class 10th and that is, name it? Yes, right. We are discussing real numbers. Okay. So, in previous session, what we have studied? We have studied number system, first part, and then second, Euclid's division lemma, and then its algorithm. Okay. Now, what we are going to study next is HCF, LCM, and questions based on the algorithm and lemma. Okay. Let's start. The very first example is your question first C of exercise 1.1 in your book, and that is 867 and 255, and what you have to do is find HCF of 867 and 255. So let's start. I have told you a simple method of division, and which one is the largest? This one, 867. So we will take it as dividend and this, the smaller value, as divisor. Now divide it, I guess 2 times, no 3 times, sorry, 3 times, okay, 765, remaining 2, zero and 1, 3 times, right? Now, what will we do? We have discussed it. This will come here. The divisor will now become dividend. So, we'll put here 255. Okay, and this is 102. So, 2 times. This is 4, 0, 2. Subtract it. 1, 5. Okay. Now, this will become what? Say it loud. This will become your dividend. 102. Now 2 times 2, 10. We are getting 0 here. So when remainder is 0, your divisor becomes the HCF. HCF of what? 51 and 102 and 102 and 255 and also 255 and 865, and here we are required to find LCM of 255 and 867. Now this is the simple procedure. Now how we will write this in the form of Euclid's division lemma? So first, let me write the equation we have studied. When A and D are 2 positive integers, mind my word, 2 positive integers, multiply by Q plus R, where value of R is what? Always must be less than B, but should be equals to or greater than 0. Okay. So, in step 1, how will we write it? We will write it like this. The larger value A, which is 867 in this case, equals to your divisor 255 multiply by quotient plus remainder. Now again your remainder, this will become your dividend. So dividend, remainder will become your divisor. So 102 multiply by the quotient here plus the remainder here 51. This is your step 2. Now as the remainder is not equal to 0, we will proceed this process to step 3. Otherwise we will terminate it here if the remainder is 0, but here remainder is not 0, so we are going to proceed this process, right? So step 3, do this question with me. Okay, now step 3 is 102, your dividend here, then 51 divisor, then quotient, and then remainder. So here remainder is 0, remainder is 0 in step 3. So divisor of step 3, that is 51, is HCF of what and what? 867 and 255, right? Now note it. Okay, let me tell you one more thing. I have told you in advance, but I am just repeating it and rewriting it again, that HCF of 867 and 255, that will be equals to HCF of what? 255 and say it louder, 102, and then again HCF of what? 102 and what? 51. Here these three pairs will get the same HCF, and that is 51. Clear? Okay, I am rubbing it. Now moving forward, we have studied number sets, real number, imaginary number, integers, natural number, whole number, and now it's time to do some exercise on it, because mathematics is all about doing exercise and questions again and again. Now number exercise. Now the first number is 5, 6, 6, 7, 8, 4, 9, 5, 1, 2. Okay, so now this number is a natural number or not? Yes, it is a natural number. A whole number or not? Yes, it is a whole number. It is an integer or not? It is an integer. It is a rational number or not? No, it's not rational number. Okay. Okay, so first example is 5, 6, 6, 6, 7, 8, 4, 9, 5, 1, 2. Okay, now this number is a whole number? Yes, it is. Natural number? Yes. Integer? Yes. And fraction number or rational number? Yes, because we can rewrite it like this: 4, 9, 5, 1, 2 divided by 1. So it is in the form of P by Q. So yes, it is rational number also. Now, the second one is it whole number? No, it's not a whole number. It does not come in the set of 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's obviously not natural number. Then is it an integer? Yes, an integer it is, and a rational number for sure. We are focusing on rational number because sometimes it's being confusing to find the rational and irrational number. So we are doing this exercise to get clear about rational and irrational and reoccurring and non-reoccurring, and as well as terminating and non-terminating. Okay, we'll find the difference of all four in this exercise only. Minus 2 by 3. It is an integer. Okay. Now 2 by 5. 2 by 5 is an integer, and which kind of integer? A negative integer. Okay. And it is also a rational number. Now root 3. If you will find out the value of root 3, then you will get numbers and numbers and numbers again after decimal. So it is never going to even terminate, and it will the decimals will never reoccur. Okay, so it is first non-terminating. It doesn't terminate. So first it's non-terminating, and the second thing, it is non-reoccurring. Non-terminating plus non-reoccurring. Now this combination is what? Nothing but irrational. So we'll call a digit, a number, as irrational number when it cannot be rewrite in form of P by Q, where Q must not equals to 0. Okay. So this kind of non-terminating and non-reoccurring numbers, decimal numbers, are the ones which are known as irrational numbers. So basically it is irrational number. Okay, now look at this one. 0.010011000111, and it terminates here. So it is what? First terminating. Okay, it is terminating. So it can be easily written in the form of P by Q. So what we will call it? Tell me. Yes, right, rational number. Okay. Now the next example is here. 0.010011000111. Now there is a pattern, but that is not reoccurring. That is not repeating. That is not 0.01010101. It's not like it. It's not like that. It's 01, then 00, then 11, then 000, then 111. There is a pattern, but it is not reoccurring. It is not repeating. So what is our answer? For sure it is non-terminating first and then non-reoccurring. So both the things are here. So what we will call it? We will call it irrational. Irrational number. Understood? Now the next one. See it carefully. 0.01010101, and how can we rewrite it when a term repeats again and again? We put a bar on the numbers that are reoccurring or repeating. In this case 0.010101. So 01 and 01 is repeating. So this is what? Obviously, first point is it is Non-terminating. What? Non-terminating. But the second point is, it is reoccurring. It's reoccurring or it's repeating. So, it is not an irrational number, mind my words, it is a rational number. So, what it is? A rational number. Okay, students? Now, again, now tell me answer of this. 53.333333 and so on. How will write it? 53.3 bar. It's simple. And this is what? It's reoccurring or it's repeating, but it's not non-terminating. So, it is rational or irrational? Right, it is rational. Okay? Now, come to this one, this pi. What we take the value of pi? We will take it like it's 22/7 and we'll take the values. But is it so? Is the value of pi is 3.14, which is very terminating? No, it is not. Okay. So, what we are going to do, all these things are clear. So, you can note it here. I will only understand you pi. Okay. So, what we are going to do, we are just knowing that whether it is terminating or non-terminating, and how we'll know it? We'll simply divide it. Okay. Like this, 22 and 7, 3 times. Okay. 1 left, 0.0, 1 time, 7, 3, 4 times, 28, remaining 2, 0, 2 times, 14, 6, remaining 0. Now you see the pattern. There is nothing which is remaining and this will go on like this. So the news is, it is irrational number. Irrational. Mind my words. Pi, which is 22/7, whose value is whose value what we usually take is 3.14, is actually an irrational number. And why so? Because it is first non-terminating and the second one was what? Answer me. Non-repeating or non-reoccurring, right? So, the number system that we have studied in earlier session, now you have cleared that one. Okay. So, let's move forward. Okay, students? Okay. So, after studying that number system, we jumped into that lemma, your mother's statement and all that. We studied example based on it, because with the help of these examples, will let us know that how a theorem or a previously proven and we will know that how a previously proven statement is going to help us to prove another statements, right? Example is, show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer, right? Now the very first step we will do after seeing these kind of question is just to write lemma, our Euclid's division lemma, without thinking. Okay. So what was that? Let a and b are two positive integers. let A and B are two which kind of positive integers such that A is greater than B. Okay, then according to what? According to what? Euclid's division lemma? A equals to, speak it out loudly with me, A equals to B multiplied by Q plus R, where value of R is what? Should maybe equals to 0 or greater than 0, but always less than B. Now, we have given B equals to what? See here 2Q, here 2Q plus 1. So, if we have to write this in this form, what is the value of B here? 2. Okay. So, as per the question, A equals to 2Q plus R, where value of R is less than 2, equals to 0 or greater than 0. So, the limit is such that the value of R equals to either 1 or 0, either 1 or 0. These are only two values that can be of R as per our boundations, the boundary lines here. Okay. Now what? Put the value of R equals to 0. ठीक है? Okay. This is our equation 1. In equation 1, now see this. A equals to 2Q plus 0, that will be equals to 2Q. See here, A equals to 2Q. Okay. Now, put the value of R equals to 1 in this equation 1. Okay. So, at, ये तो हुआ अपना, this was our value at R equals to 0 and this will be R equals to 1. At R equals to 1, A will be equals to 2Q plus 1. Okay. So, this is our third equation. Now, see the equation second and third very carefully. What is here? A equals to 2Q. Now, 2Q and Q is some integer, right? Now, multiple of any integer with 2 is nothing but what? Even number or odd number? Right. Even number, because what are even numbers? Even numbers are the numbers which are multiple of 2 or which can be divided by 2, right? These two things are same. So as per equation second, A equals to 2Q. Here 2Q is always a even positive integer. Okay, so first statement is proven. A equals to 2Q in the form of 2Q, where Q is any positive integer, even integer. Okay, sorry. So here first we have to show that every positive even integer in the form of 2q. Now a is any positive integer, it is always in the form of 2q. So we have proved this one. Now every positive even integers consecutive number is always an odd number. Okay, you can see this 1, 2, 3, 4, 5, 2, 4, 6. These are all what? Positive integers and even integers. Now 2 plus 1 will be 3, which is odd. 4 plus 1 will be 5, which is odd. So if we are having an even number and we will add 1 in it, it will always give us a odd number. So here it is proved as 2q's even positive integer. So 2q plus 1 a equals to 2q plus 1 will be what? Odd integer. Hence proved. Okay. Copy this. Okay students. I hope you have understood this particular theorem, right? So we have done some exercise of previous studied materials in today's session. Now in the next session we will do some more exercise of questions and theorems. Okay, keep watching. Thank you.